start now. Okay, good afternoon. Welcome to this lecture series of the Research Center HPC. So my name is Thomas Fahringer. I'm the coordinator of this research center, and I will host this event. Austria is a member of the PRACE program since last July. We are very thankful that we returned to the PRACE. We have been there for a few years, but then there was a delay. PRACE offers access to some of the fastest supercomputers, not only in Europe, but also in the entire world. And of course, there is, I would say, a lot of interest here by many local groups in Innsbruck, but throughout Austria, to access these systems in order to do high-impact research across many different domain sciences that require supercomputing features and resources. And for this purpose, we invited today two highly known colleagues from the Swiss National Supercomputing Center that are deeply involved in the PRACE program, in the review process, and they will tell us all about how to access these systems, how to write good proposals, and much more. But before we go into that, you see a short overview of the agenda. I would like to take the opportunity and briefly introduce the local research center HPC that inherently is related to the PRACE activities here in Innsbruck. So here's my short overview of what we are doing, why we are interested in HPC and also in PRACE. So the research center basically tries to support local groups, mostly domain scientists, that do scientific simulations, to parallelize their codes. We offer training, mostly in NPI and OpenMP, but we also support the groups through their networking activities with either other groups in Austria, but also with European groups. And one of the activities actually also comprises the PRACE program. So here you see a diagram that shows quite a reasonable number of domain scientists. So these are just the group leaders. There's also a lot of members, of course, behind every group from different faculties that are actually using the paracomputers here in Innsbruck, in Vienna, and probably some of them will also be interested to use PRACE supercomputers. So you see we cover here chemistry, pharmacy, geo and atmospheric sciences, also the faculty of mathematics, computer science, and physics, which is very large, is involved with several colleagues, the faculty of economics and statistics, and they are supported here by tools, mathematics, and computing infrastructure. The computer science is involved here. We develop compilers and runtime systems, mathematics, which is represented by several members, Alexander Ostermann, Markus Haltner, and also Michael Oberguckenberger. They basically support these teams or groups with numerical methods. And we also have a local computing center with a reasonable small computer. So we are involved also in international projects, in particular also Lean-funded projects. So we coordinated the all-scale FET HPC project, whose goal was to develop a programming paradigm for extreme-scale parallel computers. So as part of this project, a compiler for C++ has been created, a runtime system. All of that is based on C++, mostly using a C++ template approach to provide a new programming paradigm, basically to increase the productivity. And for this purpose, we tested three so-called real-world applications in order to verify the quality of our results. So here's one of them, the Ontaros oil spill simulator that has been created or is still being developed by IBM Ireland. So one of these tests towards the end of the project has been done on one of the local supercomputers in Erlangen. And here we compare basically the manual implementation that has been done in MPI against our all-scale implementation. And you see for increasing number of cores, there's not much of a performance difference, but the effort or the real value of this project was that the MPI version, of course, required several months to develop, further view from the project scale. But there's also many efforts here in Innsbruck to use at least computers, probably not yet supercomputers. So one of these efforts is led by the group of Professor Klaus Liedl. So they're doing simulation of molecular dynamics, and they explored also GPU clusters. So what you see here for this simulation, they have a reference implementation that uses 12 CPU cores that can simulate, or they can compute basically 20 nanoseconds of simulation per day. Whereas if they switch to a GPU-based version, then they use only 4 GPUs, which is not a lot, but still very impressive. The result they achieve, then they can compute up to 800 nanosecond simulation time per day. So these are some of these efforts that were quite impressive. They could also be published in high quality journals and conferences. Now coming back to the research center HPC, so what we want to support here for the local groups at the University of Innsbruck is actually real parallelization support and optimization support for the application codes that are being developed and used in Innsbruck. Then we also support research collaborations. One of the support efforts probably could be some help to write some of these PRACE proposals. And we also offer training. So this I already mentioned, like every 6 months training effort mostly focused on MPI and OpenMP, but we plan to extend that. And there's one dedicated senior scientist, Philip Schwantner, who actually is involved in all of these efforts, in particular in some hands-on work, try to improve the parallelization of some of the codes that are being used and developed here in Innsbruck. Now, what are the computers that we are using here? So we have a local, I would say, parallel computer called Layer 4 here at the University of Innsbruck that offers 20 teraflops. Then most of the groups also go to the fastest computer in Austria, which reaches 84 teraflops. And now the goal, of course, is as we are a member of the PRACE program, that we outreach for some of the PRACE supercomputers. So, and for this purpose, basically organize this event. So we have 2 distinguished guest speakers from the Swiss National Supercomputing Center, and you will tell us all about what are the opportunities for us to access it, how to write these proposals, and also the procedure in general. And with that, I would like to hand over the stage to the first invited speaker, to Dr. Maria Grazia Giuffreda. Can you switch the presentation? She obtained her PhD in computational chemistry in Belgium, followed by a postdoc at ETH Zurich in physical chemistry department. Then since 2006, she's working at ETH Zurich, the Swiss National Supercomputing Center. Since 2013, you are an associate director and head of the user engagement and support unit. And you're also responsible for the user lab program of the CSCS National and Tier 0 calls for proposals. And finally, you're also a member of the PRACE Board of Directors. So you will give a presentation about the peer review process and proposal taking.
Can I have the... So thank you very much for inviting us to beautiful Innsbruck. And we will, the reason why we both come from the Swiss National Supercomputer Center is really by chance. And PRACE Days 2018 in Ljubljana, we were asked to give a presentation on the peer review process, and I was the chosen one to do that. And then the Access Committee decided that it would have been a good idea to actually try to give a presentation on how to write a proper proposal. And then Luca was chosen for that. And as I said, it's by chance that we both come from Switzerland. And it's not because we are very close, but we then decided to both come because it's better that you also change the speaker rather than having me talking for 1 hour about everything. So what I'm going to do is to explain a little bit more in detail the peer review process of PRACE for the Tier 0 proposal, and to explain the various steps that your proposal will go through once you have applied. And then Luca, who also is responsible at CSES for the technical review of the proposals, will guide you through how to write a proposal that will have chances to be actually accepted. So PRACE provides a federated European supercomputing infrastructure. I think you all know that because now Austria has come back into PRACE and wants to enable large computational projects. So here I am talking mainly, or I should say exclusively, of the tier 0 call for proposals. So we are talking about the largest tier 0 infrastructure in Europe. And there is a very transparent peer review process that has been put in place, where it is mainly based on scientific excellence and then, of course, feasibility of what you want to do on the machine of your choice. So you might have the most fantastic science, but if your code cannot run on any of these systems, there is nothing really that can be done, but maybe sit with you and discuss how we can better help you to port your code into the tier 0 calls. This is an overview of the calls. The reason why I still have call 18 is because this is still an open call. Now they are completing the reviewing process, and in March the Access Committee will meet to decide on the proposals. But the next call, call 19, is already been open. No, it's already been announced, not open, sorry. It will be open by 5th of March, roughly. I think there might be 1 or 2 days change, but not more than that. And it will close the 30th of April. It means that you usually have about 2 months, 6 weeks at least, to actually write your proposals. And then the allocation period will be 1st of October 2019. I will assume that very shortly they will also announce the call after that. As soon as call 18 will close, they probably will put out already the information for call 20. So project access, what the duration, usually, typically, you can submit yearly proposals, so for to get resources for 1 year, but there is also the option for 24 or 36 months. Even though if you submit a multi-year project, you have to be aware that you will be asked, or not you, but the PI of the project will be asked to go to Brussels and present the results after 1 year. And usually the Access Committee gets quite upset if the PIs do not show up and send simply co-workers. So the Access Committee really wants to see the principal investigator to show up and present the results. And this will have to be done twice if you apply for 3 years proposal. This is just out as an information. You know, the Center of Excellence, the European Commission have approved the new Center of has funded the new Center of Excellence, and this Center of Excellence actually can simply ask to get access to all the machine, the tier 0 system in PRACE with this 0.5% of the resources in every call. So this refers to the previous one, but actually if you go on the European web page, you will have the list of the new Center of Excellence. So who can apply? Any scientist who has an employment contract with an academic institution can apply as a principal investigator. Of course, in PRACE, these resources are mainly for open science, so non-military or secret science can be run on this machine, and you have to be aware that you can certainly submit your proposal in multiple calls, but you have to declare it, and if your proposal has been granted already in another call, cannot be granted also in PRACE. So double granting is really not permitted and shouldn't be followed. So here I machines available in tier 0. So every country, there are 5 hosting members, France, Spain, Germany, Italy, and Switzerland, that they put into the pool the big systems. So you will have, there are 2 systems for France, because one is on Sky Lake and the other one is KNL. And for France, the threshold, I think, is 15 or 20 million core hours. I don't remember by how, things might be changed a little bit, but you have to be aware that when PRACE open a call, there's detailed documentation of what is offered and what are the conditions. So every center, for example, will tell you that if you want to apply to the Swiss machine, so this Pitzdine that Thomas had in the previous slide, you will have to come with the codes that can use GPUs, because the machine is GPU accelerated. You will have to come with a resource allocation that is above the 1 million node hours, so 68 million core hours. So there are conditions that you have to look into when you apply for a specific system. Then there are the German machines, so Hazelland in Stuttgart, Jewels in Munich, and Supermooc in Munich. Then there is the Italian machine, Marconi Broadwell and Marconi KNL, Mare Nostrum, which is the Spanish machine, and Pitzdine, that is the Swiss machine. Now, all these machines are, all the specifications for these machines are available. So there is the terms of reference and the description of the call, where you have all the details. So there is, I mean, it's really very well documented. So I doubt that there will be something that you cannot find there, but otherwise you can always contact any of the centers where you are where they have the machine you are interested in, and they will get in contact with you and they answer to all the questions that you might have. So this is the peer review process, because this is the part I'm going to describe a little bit more in detail. There is an admin check. So your proposal has to contain all mandatory items, because otherwise will be rejected at the administrative level and nothing else will happen. You'll just have to wait for the next call to apply again. But once you have passed the admin check, then every proposal is assigned to 2 rapporteurs from the Access Committee. The Access Committee is the committee that in the end will meet to rank the proposal. Then there is the scientific assessment of the proposals. At the same time, there is the technical assessment, and the technical assessment is done by the centers where you have applied. So where the machine you have applied is actually hosted. After that, the rapporteur has to assess a grading process, and they have to come up with a final ranking. And then it's these resource allocation panels that, by following the recommendation of the Access Committee and the various rules or agreements within the various hosting members, will distribute the resources. And then the board of directors, they will simply approve this. So in more details, step by step. As I said, administrative check simply means that you have to follow the criteria described to write your proposal. So you have to have all the items, otherwise your proposal will be rejected for a silly reason, because these are basically silly reasons. If you forget to put your publication list or your CV, or if you don't have any technical data, I mean, it means that you have either you didn't put the proposal together in the proper way, or you simply forgot. Then you have the technical assessment. As I said, the technical assessment is done by the center hosting the machine you have applied to. So what is very important is that you always start with a preparatory access, because the preparatory access will allow you to collect the data on the system you are interested in. And will also help you if it's not clear what is that these technical data are, and that is, and then Luca might explain a bit better later. You will simply get the help of the technical people of the center helping you collecting this data. So it is important that you come with a preparatory access, also because when you write your proposal, you will be asked to give the number of your preparatory access. Now, you might not have a need for a preparatory access via PRACE because you already have access to that machine. That's fine, as long as you can provide the data on the machine you are interested in. Then the scientific assessment. This is, each proposal will be judged based on the scientific merit, the soundness of your methods, and also you have to show that your methods is the best available to do what you intended to do. And then you have to have appropriate timelines and resource requests, meaning please do not give random numbers. Your resource request needs to be justified by all the technical data that you are giving, so that you actually prove that your problem is really in need of 2 million node hours of bits diet to be solved. And it's not just that because the threshold is 1 million, you put 1 million. Because the technical reviewers will try to reproduce your number, and if your numbers cannot be reproduced or they do not actually overlap, then there is a problem. And then your proposal might be simply discharged because it doesn't need the resources needed. And then, of course, I mean, you have to put down the track or the qualification, expertise, the publication record, and so on. Now, the Access Committee. So the Access Committee is usually as a minimum of 15 members per call. Sometimes it can also be 17 people, and then there are 2 members that they are acting for each proposal as Rapporteur 1 and Rapporteur 2. They have to suggest scientific reviewers for the proposals, and then they have to discuss among themselves if there are discrepancies, and then they have to come to a common grade. And then they will discuss this at the Access Committee. Of course, scientific excellence is always the most important criteria that they will base the decision upon. The Access Committee has now has to make, I mean, they sit twice a year because we have, of course, 2 calls per year, and then they have to really every single proposal will be discussed in details. Of course, there are proposals that they are more straightforward because maybe everything is really more or less perfect or as perfect as can be. But there are several proposals that need to be discussed. And so during this panel meeting, which is a meeting of 3 days, so you understand they really check, they really discuss every proposal, they will come with a final ranking. And the Access Committee goes as such. The Rapporteur 1 will discuss the proposal. What are the strengths? What are the weaknesses of the proposal? What is the relevance of this proposal? Then the technical reviewers are always asked whether the proposal is ready to run on the machine that have been applied upon. Then there is also the Rapporteur 2 that also has, because he also has an opinion, and even though he has discussed with the Rapporteur 1, he still brings additional comments. After that, all members of the Access Committee are discussing these proposals, and it's up to the Rapporteur 1 to propose a ranking for this proposal. And of course, if the majority of the panel of the Access Committee agrees with the ranking, that's the ranking that is given. And then they move to the next proposal. The proposals, in the end, all the proposals that have that they are above the threshold where they should be accepted are sort of rediscussed and ranked also to, normalized a little bit among the various disciplines. but only those that have already passed the threshold that from here on we are actually going to accept these proposals. The final step of the peer review process is this resource allocation panel, and this is basically a panel where for sure the chair and the vice chair of the access committee are sitting, then the representative of the center, but okay, the deputies of the directors, I should say, of the hosting members, because these are the people that they are actually giving the resources, and the technical teams. And usually, I mean, up to now, it must be said that usually the RAS follows the recommendation of the access committee. They don't really need to change this recommendation, because this recommendation is based on scientific merit and all the various considerations. Now what can happen in this meeting is that once a specific machine has been filled, if there are still valid, still accepted proposals that they have applied for that machine, this proposal must be granted on different systems. So not the original systems that they have applied for. The thing goes as, if there are resources still available on another system, of course this exercise can be done, but this exercise requires the technical people to be able to say, okay, based on the technical comments of the colleagues and based on the codes that they want to use, okay, it was applying on Mare Nostrum, but GROMAX, I'm just saying for as an example, is a code that Switzerland knows works very well on GPUs, so maybe we can look at it and we can move the proposals on PITSDYNE. Also because PITSDYNE usually is the machine that is never fully allocated because of, I mean, GPU's requirement is mandatory. So this is the exercise that needs to be done in this final step. Try to allocate all the proposals that have been above the threshold where they were accepted. Of course, it can happen that some proposals that have been accepted will not be granted because there are no resources available anymore. And then there is very little that, I mean, the PI might be upset, might be even protest, but if there are no resources available, there are no resources available. So this is why you should always try to apply, not necessarily for the easiest machine, but also to think a bit more broadly whether your application could run also on a, as I said, on a system like PITSDYNE or a system like KNL. I mean, these architectures that they are a bit more special, but could still give a lot of resources. Now, the scientific assessment, this is the last thing I will be comment, and then I give the stage to Luca. So the scientific assessment is basically what they are going to do here, the access committee, is to look at the excellence. So is this proposal really scientifically valid? Do these scientists have a problem that requires tier 0 resources to be solved, and also that has an impact on the scientific world? Please remember that we are talking about the tier 0 calls. So these are the last calls in the hierarchy. So I mean, if your problem really can be solved on your local system, you should go for your local system. It's much easier. But if you have a really challenging scientific problems that you would like to try to solve, because risk is not a problem. I mean, the access committee understand that you are trying to solve a risky problems. As long as it's a valuable problem that you want to address, they will consider it. Then you have, okay, there must be some measure of novelty in this proposal. We all know that scientists have their own line of research, and this is where they are putting their effort. but they also should come up from time to time with challenging problems that are a bit outside the standard research path. And this is what the novelty and means here. Then is the proposal, PRACE proposals are, they are described quite specifically. So once again, you have to spend some time in reading the calls to understand what kind of problem you should submit in a PRACE TR0 call. Methodology. Also here, ideally, the Access Committee, Access Committee are top scientists from all over the world. They would like also to see that researchers are making an effort to use the best methodology available and not something that they have been used for 30 years and they don't want to change. Because that's not really the idea. Unless you can prove that your methodology is the best available, you should be a bit more open-minded as well. Even though, as I said, we all understand scientists have their own line of research, they trust their code, they know what they are doing, and ideally they don't want to change. But sometimes change is good. And then, of course, you have to also have a dissemination plan in your proposals. Usually we all expect that proposal will be followed by, your research will be followed by publications. And when you publish or present your proposals, or your results, please be aware that PRACE really expects you to acknowledge having received resources from PRACE. And if you don't do that, especially in your publication, this will have an impact on if you submit other projects in the future. Because if you do not, the only way PRACE, but also computer centers, also Switzerland does the same. The only way we can prove that we are doing a successful job is by proving that we have scientists getting interesting results that they are published. So if we are not acknowledged in the publications, there is no other way we can prove that we have done our job. And this is the same for PRACE. If there is no acknowledgement of getting the resources via PRACE, it's a bit sad for PRACE because they cannot prove that they are actually doing something good for the scientists. And then, of course, you have to ensure that you have everything that you need to be successful in your proposal, which means also the resources, human resources, and everything. Because submitting an amazing proposals, but then you don't have any student or any postdoc or anybody to work on it, and so you will not be able to use the resources, will also be not very good for following proposals. So you have to see some, they do ask for the history of PIs. And with this, I conclude my presentations and I leave the stage to Luca. I don't know if you prefer to ask questions now or we first go through the entire presentation and then open the discussions. I don't know how.
We have the first round of questions.
Okay.
Before we move on. So first of all, thank you very much. Now there's the opportunity for you to ask questions. So I have the first question. You said there is specific calls once in a while, limited to what? To domain science or a subset of the PRACE computers? Can there be a call only for biology?
No. They don't do, no, PRACE, at least up to now, PRACE has never opened calls for specific domains. So the calls are for all scientists. Can also be from economy or whatever, as long as they comply with the requirement of the tier 0 description. But it's not per domain.
But you mentioned something, if there is a specific call, what do you mean by specific call? Is it always generic or is it limited once in a while to, I don't know, a subset of
No.
computers?
The specific calls, maybe for specific calls, I meant that the call 18 or call 19. I mean, but PRACE has 2 calls per year so far, as far as I can remember, and I'm following PRACE for quite some time. So they have 2 calls for the tier 0 allocations, and these calls are more or less always the same. The description is always the same. So you can go and there are documents that they are published. What you can also look at are the preparatory access. So they have the preparatory access meant to simply prepare for the tier 0 submission, and then they have preparatory access that they are called B, C, and D, that they are a bit different, because the B gives you 6 months, first of all gives you 6 months rather than the 2 months for preparing, and because it requires from your part a little bit of tuning and optimizing of your code, and this will be done on your own. Then there is a type C where you can ask for help from the centers, but you have to be aware that the tier 0 are not necessarily involved in this. So for example, Switzerland doesn't do that, neither type C or type D, because it's a bit, I don't know, it's a question of flavor, whether one likes it or not. But they do have different preparatory access, and maybe one of these preparatory access might fit your need, but these are for very small allocations. Very, very small, not even tier 1 allocation. These are very small allocations just to help you testing your codes, importing your codes, or optimizing your codes, but they don't give you resources that will allow you to do production.
Then I have another question.
Yeah.
If I prepare a proposal, can I structure it in such a way that I can say, okay, my simulation would run on machine 2, but also on 7 and 5. So to avoid a scenario where most proposals go on machine 5, and I also targeted machine 5 and I get rejected because the quantum was used up too fast.
I think that my personal advice is look at the pool of machines available, and if there is more than one that would fit your purpose, ask for a preparatory access on all of them and collect your data on all of them, because once you know how to do it in one system, it will be pretty much similar also on the other systems, but you will increase your chance, because as I said, if Mare Nostrum is gone by the time your proposal arrives, then you can still be considered for the, I don't know, Curie, or for whatever, Hazel N, or whatever other machine.
Yeah. But if you ask for one machine in the proposal, and this one was so competitive that you just didn't make it, then maybe you are lucky and the commission moves you, but
Yes.
in usual cases you are out. Right?
No, if the proposal is really valid, the Access Committee chair will argue to try to allocate the proposal. So he will even argue with the center and ask if there is any center that would be willing to give a little bit more resources to accommodate such proposal. So if the proposal is really scientific valid, there will be a discussion to have the proposal granted. But if you are really out of luck and there is nothing anybody can do, but you will know that, because in the final statement they will tell you, okay, your proposal was fantastic. Now I am oversimplifying. Your proposal was perfect, but unfortunately at the time even though, you know, I mean, ranking means also that the scientific merit is going down. But they will argue, the Access Committee chair will argue for a proposal granted to be allocated.
Is there some other questions?
Yeah, I was wondering regarding the eligibility of PI and collaborators. Does every one of them have to reside in the EU or in the PRACE kind of reside in countries, or is it also allowed that co-workers are?
Sorry, I didn't understand. Sorry.
So the question is about eligibility for the PI.
Yes.
He has to be affiliated with one of
PIs from the United States or China or Japan. There is no such a limitation. Of course, I would assume that if it's my assumption that if you have two proposals that they are really equally good, they will favor the European one. I mean, at pari merito, at the same merit, they will favor the European one. But the PRACE calls are not restricted to.
Just to define our ranking, you are referring to the final ranking, and if it is a third country or not, then you have a certain amount of resources.
You have the only unfortunate thing is that there are certain rules that the hosting members have agreed upon, like this the Giuffreda, that the members that they are paying more should also get more than others. But to be very honest, not all hosting members are following these rules. They cannot care less. They want to have the best science wherever that comes from.
I have a small question. Say hypothetically, I have two applications that are both candidates for being run on PRACE machines.
Yes.
I will file for preparatory access. Can I, assuming I have the manpower to investigate both of them, is there a limit in terms of the number of proposals I can hand in, or can I do both at the same time?
You can do, and you can also submit as many proposals as you want as a PI, as long as you clearly state in your proposals that these are different problems. Because otherwise, if you just split the same problem in 20 different things, they will not accept your proposal. But if these are from the same PI, different scientific problems, yes. And at the preparatory level, you can apply for one preparatory project and investigate whatever you want. If you, as you said, you have the manpower to investigate 4 different problems, that's absolutely up to you. Because what is important, you have to realize what is important is not the number of your preparatory project. What is important is that in the end, in your proposal, you have the valid technical data to support your request, and that's it. If you have that, you can also not even mention your preparatory project, but if they see that you have the results on PITS dying, that this data makes sense, that's it.
So then, one more question. If someone submits a proposal and it gets rejected, he gets an evaluation report that
Yep.
hopefully is reasonably detailed. But then the question is, let's assume the reviewers were picky on the numerical methods and said, why don't you use a different numerical method? Then you change to that method, resubmit. How predictable is that? I mean, could that be the next reviewers that say the total opposite what the first bunch of reviewers said in the first round of the submission?
Well, no, then I wouldn't consider a risk, because you have to realize the access committee members, they are not changing dramatically in every call. Half of them at least are the same, and they will remember whatever has been discussed in the previous call. They are not that old that, you know, in 6 months they will forget everything. But I mean, I don't know, usually it's not that, I mean, if a proposal is resubmitted after being rejected, of course it depends on the reason of rejection. If there was no machine available, okay, bad luck. You can resubmit more or less the same proposal, even though you should still trying to improve, because it means that it was still lower in the ranking, in the scientific ranking, and so you should try to improve it such that it jumps up. But if a proposal has been rejected, they will carefully look into it if it's resubmitted, and try to see what, they will even probably bring up the old proposal and compare with the new one.
But somehow with that procedure, it looks like I can gradually improve, right? I get feedback, and if I fix it or improve towards it, my chances probably...
Well, sure. I mean, that's the idea of giving the reviews, the comments, I mean, is that you read what are the problems, also from the panelists, And they will tell you why the proposal has been rejected, and so you should improve on this, that, and that. They are trying to be detailed because this panel really is adamant that the process should be transparent. And being transparent means that information needs to be provided to the applicants.
Are there other questions? Are there any public records of statistics of accepted and rejected proposals?
I don't know. I mean, I should check on the PRACE web page whether they have published something, but I would assume yes, but I don't know I think that in the calls that since CSES has been involved, there is a rejection rate of 40–30%. But I can check and I can forward the information to Thomas if I find it.
Okay, so let's say. And next is Dr. Luca Marsella, who will explain how to create a good proposal. I think that's important. So a short information about his bio. He graduated in physics at the University of Cagliari, and he holds a PhD in statistical and biological physics from the International School of Advanced Studies in Trieste. He has been working in various fields of computational material science, computational biophysics at the University of Padua, at the École Normale Supérieure in Lyon, and also at the University of Split. And he currently works as a HPC technical advisor at the Swiss National Supercomputing Center in Lugano, where he's responsible for maintaining the scientific software applications portfolio and providing support to the CSCS users.
Okay, thank you very much. So, as Maria Grazia already mentioned, we will go through the proposal template that you will need in order to submit your PRACE application. At the end of the presentation, there is a slide with further information and documentation with the links to the PRACE webpage where you can find the actual proposal template. It's a doc format. You can find a PDF with the technical guidelines for applicants that Maria Grazia already mentioned, that I really advise you to read in detail because it mentions all the systems and the limitations, in the sense that the minimum amount of allocation that you should request, the maximum amount of nodes that you can run on, all the possible storage facilities. So this is really important that before writing down your application, you already know what you can ask for on the different targeted machines. Now, the proposal template will go through different sections. It's quite structured. And the access committee, so the committee that decides on the proposals, is, as stated, that applicants should provide all the information on all the subsections. But of course, there is the possibility that some of this information is missing. Then, if you leave it empty, you should provide a reason. So everything is possible, just justify that. So also you should consider that your proposal will be reviewed by a pool of scientists of different domains. Everybody has to vote your proposal. So your proposal should be, let's say, technical in a certain way, in the sense that people of the field could understand, but it should also be understandable from a broader audience of scientists. So take it into account, because people will also evaluate the impact of your proposed science during the complete evaluation. Now, let's start with the initial part of the proposal. Deals with the key contribution in terms of scientific, societal, technological contribution. So you should outline here what is the societal importance of your project. So what are the outcomes and the benefits for the whole society? So how is high-performance computing helping to achieve these goals? So what is the relevance of these tier 0, so high-level HPC resources? Are they really necessary? So what are the major expected outcomes? These are, I think in general, these topics are always requested in scientific proposals, because in order to justify the resources that you're given, you should also have an impact. Now, it's also essential to state the importance of the scientific problem. So you need to justify the scientific relevance in order to access the resources. So you need to describe the research, the main technical advances that you are going to achieve with such a high-level HPC allocation that the PRACE consortium is providing. There are also there is also the possibility to have industrial partners, so applicants can be also from industries. The point is that also industrial partners are subject to the same rules of academic partners. So they need to have to stress the potential and the growth that is coming out of the proposal, not only for the industry, let's say, for their own benefit, but for the society as a whole. That's a key point, because we had in the past some collaborations between academia and industry, and these are welcome, as far as there is an outcome for a benefit for the society and not just for the business. The justification of the requested resources must be clearly linked to the software performance evaluation. So this is something that sometimes is forgotten. It is at the beginning so that you don't forget. You are requesting some resources, computational resources, in order to get to some results. And during the next slide, you will see that you need to provide a measure of what you're going to require, depending on the type of code that you have chosen, the target system, the HPC system that you have chosen, and out of that, then you can, depending on your project management plan, you can plan how much resources are you going to use. And in this way, if this resource plan is clear enough, there will be no trouble in order to justify your request. And that's the part that I was mentioning, the overview of the project. So in terms of your scientific, the scientific objectives and challenges of your project, you need to justify the choice of the computational methods that you're using. So the choice of the code, for instance, the choice of the libraries that you are going to use, justify if there are alternatives, why are you choosing that specific one. Of course, so the reply, let's say a statement like, we've always been doing that in our lab, it's not really acceptable. So at this time, there are many alternatives of codes, community codes, let's say, that each domain science, the domain field has developed. There are domain scientists working actively in developing code. So you have actually to prove that if you have your own developed code, then you have some benefits out of that. And then you have also to state on the interdisciplinary value of your proposal, because that's also an aspect that is evaluated by the committee. So cross-disciplinary collaborations, cross-domain collaborations are always welcome. Now we come to a more technical part, because that was the kind of introduction of the proposal. So the broad scientific scope with the methods, with the expected results, the benefits. Now, the technical part of the proposal comes here. You have to take into account you're asking for facilities, computational facilities. You need to know, you need to be aware of what you're asking for. So the committee has asked in the past that the researchers are aware of the numerical methods that are behind the codes that they're using. So that comes here, the part called validation, verification, state of the art. So you need to describe the validity of the simulations, the predictions that are coming out of your simulations. Validity means providing references to publication, addressing the reproducibility of these simulations, addressing the numerical stability of these results, and let's say sensitivity analysis. All of these can be found in the next sections, validation, verification, sensitivity analysis, and comparison with state of the art. So let's go one by one. You can stop me at any time if you prefer, if you have a compelling question. The validation means to validate your model against experiments or any other established set of data, anything available also in existing publications. You don't need to rerun all the possible, let's say, knowledge, of course. You have to just cite the good papers in case you have already some established method with established validated results. Of course, if you are developing something new, then you should provide more details about the possible validations and the existing reference data for your method. The verification, so the numerical consistency of your method, the numerical verifications of your computational method, you should provide then evidence of existing verifications if you're using some community codes already established, or if you're developing your own code, you should at least show that your method has been numerically consistent. So let's say the convergence of your algorithm is proven. You can show some reasonable data about that or from your publications. And then sensitivity analysis, uncertainty quantification. So people should also be aware of that in the sense this is specifically important for fields like computational fluid dynamics, just to mention one. But any algorithm, of course, has done so for any algorithm, it is important to have the uncertainty quantification coming out of the initial conditions, let's say. So you should provide some sensitivity analysis, or you should provide, let's say, already existing set of data that is showing that the code that you're using has been going through the sensitivity analysis. And the data-driven uncertainty quantification is encouraged. So you're always asked to provide data, just not statements. Data or to cite the, to reference the important publications for that. And in case of multi-physics, so multi-scale problems that involve several different orders of magnitude in simulations, also the uncertainty of the methods and the software that is used is desirable in your project. So each component of your multi-scale simulation should be analyzed in this sense. And then something that I mentioned already, so the comparison with the state of the art. So you should be aware that your study will be placed in the context of competing works, so competing proposals, and then you should explain what are the advantages of the approach that you have chosen, the code that you have chosen, and the drawbacks as well. So the goal is to make the committee that is evaluating your proposal, to make the committee see that you are aware of the strengths of your method and also the weaknesses, and that you can actually deal with them in a confident way. Now, another section of the proposal template is this description of the software and the attributes of the software, so like libraries, external libraries, for instance, that you might use. Now, here, the description of the software that will be used will include a discussion also of the state of the art, something that is quite important and people tend to forget. Because in general, it is actually very easy to state that your group will use a certain software, but it's actually not so easy sometimes to justify why and what are the alternatives and why do you choose exactly this. So in terms of software, you should describe all the codes that you're using in the proposal, not only, let's say, a main code, but if you're using some post-processing code, some pre-processing, sometimes this is custom done. These are programs sometimes that are optimized locally in the lab. These are also important if they're going to run on the target HPC system, the Tier 0 system, they should be mentioned, because the HPC centers, they want to know what you're going to run during your project. And then you should justify the choices and describe the alternatives. You shouldn't be scared by this in the sense, of course, there might be many alternatives, but at least you should try to do that in a sense to let people understand that you're not just using this because of historical tradition of your lab, but there is also some logic behind that, because otherwise there might be other codes that perform better than yours. There might be other choices that are better for your specific scientific problem. Then libraries. So libraries required by your production analysis software, for instance, algorithms, numerical techniques, which programming languages are behind your code and the libraries that you're using. Of course, if you use established libraries, numerical libraries for linear algebra or other types of established libraries, again, you should cite the relevant papers. You should show that you are aware of the benefit of these libraries, that these libraries are bringing to your computational project. Parallel programming models, this is especially important because we are talking about different target systems that you have in the PRACE pool of tier 0 machines. So you should state which approach are you using for parallel computing. Is it a message passing interface, so the distributed memory? Is it a hybrid OpenMP MPI, OpenMP with pthreads? Is it your code based on CUDA to run on GPU accelerators, or are you using instead OpenACC to accelerate your code? So all these programming models should be stated in the software and attributes section, as well as input and output. So I/O requirements. This is a bottleneck in general of some simulations. So this is especially important, and the amount of data that you produced sometimes is really enormous. So that's the section where you need to outline these requirements, because the amount, the size, the bandwidth of the input files, the restart, and the output files are essential for the computing center in order to evaluate the impact of your work on the everyday routine, let's say, of the machine. So you should describe your I/O strategy. So you're generating how many files in general after a job, after your typical simulation, with which frequency, with which read and write rates, and what is your data management plan then? Because you need also to understand that you will have to post-process this data, and probably if you can't do that in the machine, you need to transfer the data. So you have to take into account also this part. And one of the important things is also the behavior of your code during the execution, because you should also let the center know if you have spikes of huge bandwidth requests or output, let's say, of enormous data files, or for instance, some codes that I remember now using a lot of distributed memory MPI tasks, generating an enormous amount of file each one, so really challenging the file systems used. And the center needs to know that in advance. And again, the restart overhead. So for instance, of course, you can't have the system for a week. So you need to have checkpoints, restart points in general, because the number of hours that you can run continuously is generally limited in computing centers due to fair usage. And you are asked to specify that as well, and also to specify if this has an impact as an overhead in your execution. Now we come to something that I was already mentioning, so the data storage, analysis, and visualization. So this means post-processing in general. So the project workflow, you should include a timeline for data analysis and visualization. That's something typically done nowadays. So in order to analyze the data, you want to visualize them in general. So something called in situ visualization that you can do on the computing center, but sometimes people tend to move the data as well. So you need to identify all the potential bottlenecks that come from this analysis. And the software workflow solution, so pre- and post-processing scripts that automate to run your simulation. Sometimes we have groups that are applying, and they use then a complicated Python interface in order to submit their jobs. That's perfectly fine as far as this doesn't create a overhead on the local file system or on the scheduler, because there are, of course, approaches to avoid such problems, and this should be highlighted in case it might create troubles at runtime. And the I/O requirements for data analysis and visualization, so you should here highlight if there is any exceptional I/O need, and you should provide data for systems that will be simulated in this case, in the sense how many particles are you going to visualize, which type of visualization program are you going to use, or do you plan to use? Is it already being used at the center in the machine that you're targeting? So all of these should be planned in advance. So looking at the technical guidelines for applicant, you can find the I/O limits and ranges that you have in terms of storage on the systems. Looking on the websites of the center, you can see if any visualization post-processing code is already available, and so you can plan better your project. The software performance now, I think this is the core of the resource request, because as I mentioned before, the resource request will be based on the software performance. So the performance that your code is actually showing on the target system. So the information on software performance, therefore, is mandatory. So there is no way you can avoid to provide that. In the past, there have been cases in which some applicants were submitting performance that was obtained on different systems, supposed to be similar. This is something that is discouraged. So unless the system is really the same. But it's preferable that you apply, if you don't have an account, as a preparatory access to the target system, and then you ask the technical help of the support staff of the system in order to perform your performance, to run your performance analysis. Then the performance should measure the time to solution, let's say, of your production code. Now, in general, you will be requested, if you had a preparatory access on the system, to mention that, as Grazia already reported in the previous, in the first half of the presentation. And also, you can have already had a previous tier 0 proposal, so you can have already resources, then you should mention that as well, because the history of your proposals will be also taken into account. If the preparatory host machine then is different from target machine, you need to specify why then you presented the data, the performance data that was computed on a different system. Why do you think this is compatible, relevant? So again, you should justify if there is anything that is not as expected. And then you should report briefly a conversion factor, if any, from the preparatory test machine to the machine that you are applying for. In theory, you should do your testing. This is strongly advised on the machine that you are targeting. If there is any reason that this is not possible, then you should also take into account any conversion factor, because the allocation then might be changed. Now, how to measure the performance? So you should quantify the performance of your project. Then, the data must be representative to the entire workflow of the project proposed. It must refer to the main application code, and you should start with the scalability test. So you should check for the most efficient job size for your planned simulations that depend on the system that you use, not only on the code that you have chosen. And the performance then should be linked to the request of computing resources, in the sense, once you've chosen a certain job size, say a certain amount of nodes that will be used in production, you should use that time to solution computed for that number of nodes to extrapolate the total amount of resources that you will need to perform to complete your study. This should be clearly linked, should be pretty easy, not convoluted, because otherwise it gets more difficult to actually evaluate your request. So the estimates based on related codes or on only a subset of the code will not be accepted. You need really to focus on the full application, the whole software that you're using. And the data must refer to the targeted system in production. So it should, if it is not the same system, it must have a comparable size, a software stack, and the same architecture, and also the interconnect, so the network. If you are in doubt of the data, it's always advisable that you contact the computing center, because the support staff will reply to you. So computing centers on the web page have the contact information, so please use that. Don't assume anything for granted, just ask. It's better to ask more than actually put less information and then maybe be rejected just because you neglected to ask. You don't need to be ashamed of writing an email and asking. In terms of performance results, the template is quite detailed, so we'll go through these metrics. Let's say strong, weak scalability, the precision of your code, the time to solution, the system scale, the measurement mechanism, memory usage, and then there is an optional part at the end. So strong and weak scalability it has been stressed over the past calls for proposals that you should start with a scaling analysis of your problem. You have a certain test case input, let's say data set, and then you have a code, and then you want to test this code on the system. So with this specific input files and see what is the best size, the best, let's say, job size in order to have the best performance. And then you start see what is the scaling behavior. You shouldn't cheat. You should start with the minimum amount of resources that is requested to run. Sometimes there is a limitation due to memory. Okay, then you should specify why, if you don't start with one core or one node on the system, you start with 10 nodes, I don't know, I'm just speculating, and then you should justify exactly because I need this amount of memory that is not available using a certain only one node. So it should be justified. Then weak or strong scaling. Sometimes you can put both of them. Sometimes they are not relevant for the specific problem. For instance, if you study a biomolecular system, then it has a certain size. You cannot really study an ensemble out of that. So it makes sense to have a strong scaling. But if you study ensembles, then you probably show weak scaling. You just increase the size of your ensemble. So you should anyway state why you're doing one or the other, one strong or weak. Or if you are, let's say, putting both of them, this will be welcome, but it depends on the specific test. You should state which precision you're using in your simulation, single precision, mixed precision, and then, because this, of course, affects the performance. And then the time to solution, which is quite, I would say, the most important element here to evaluate then the final resource request, because, of course, there are several ways to report the time to solution, but you can normalize that per iteration, per number of cores, size of the problem, but it should be easily understandable in the sense it should be the reported time per iteration times the number of cores divided by the computational elements should give the amount of resources that are needed to perform at the best job size that you've chosen due to scalability, this benchmark that you are presenting. Out of this benchmark, you will use this as a unit in order to request the whole amount of resources. So you should state that clearly. So the it can be normalized as total time to solution, as I mentioned already, and then you should justify the choice of the code again. So comparison with existing codes, the methods, any other scientifically rigorous argumentation should be also pointed out. Then the system scale, so the performance should be measured on the full scale system, so the real system that you're going to study. You don't have to spend a lot of computational resources to do that. Sometimes a few minutes are enough to get a good performance time to solution if the test set has been set appropriately. For instance, the biomolecule that I mentioned before, if the system has been already equilibrated, as they say, as people used to say, the amount of time that you will use to simulate then the biomolecule will be linear with the time that you actually run the system. So it will be already enough to show that for a few minutes and then can be extrapolated. In other cases, there are similar ways to evaluate. So you won't spend a lot of resources just for this, but you should do that. Then the measurement mechanism, you can use the timers inside of the application. Sometimes they have it. You can use some static analysis too. You can use the scheduler time. You can use some performance modeling tool, flop counts, whatever you have. It's better that you put in the proposal. Again, asking if in case of doubt to the computing center experts. And then the memory usage. This is also a bottleneck sometimes because you should specify which requirements of memory per node or per core are used by your code, because depending on the size of the computational system that you're using, this might really forbid you to run on a certain, at scale, let's say, especially some demanding codes in material science sometimes are very limited, and you are compelled to run on a single core on a whole node because of a huge memory requirement. So this is something that the researcher applying should know. Otherwise, you end up going on a HPC system and then you just complain because you cannot run at scale just because of memory limitation. That's not an argument at that point. Then the optional item is the percentage of available peak performance In order to compute that, sometimes it's not an easy number to compute. So the access committee was insisting, if possible, to have that. And that's why they marked that optional. So optional means if you can't achieve to get that, then you simply state it was not possible. But you need to at least make an effort, because the computing centers, again, can help you. Because there are some tools that can help you doing that if the code doesn't already give you this number. Some codes, community codes, already put in the output the amount of flops that have been used in your simulation. The computing center knows which is the theoretical peak performance of the system, so you can easily compare the two and give a number. Then, in case of a request of help, the PRACE review office is available for getting the request in order to contact the high-level support team of the different centers, but that should be done in advance. So we state here at least 1 month before the deadline of the proposal submission. You can also contact directly the centers, of course, and that would also work fine. Alternative metrics are also accepted, let's say, as far as you can get them from any tool that you have running in your specific code. And then, just to conclude, I want to give you some examples of the performance reporting. So, again, you should start the scaling with a minimum simulation size that is available due to memory limitations, and finish with the maximum numbers suitable for application. In general, we tend to say that you should follow the scalability. You should look at the speed up. When you reach an efficiency that is below 50%, you should probably stop. So the efficiency means the ratio between your actual speed up and the ideal, the linear one. Then you should mark the number of cores expected to perform your simulations. So on the y-axis, you should put the time to solution, for instance, the normalized one, versus the minimum number of cores on the x-axis. And you should also put, apart from a plot with scalability, also a table with the timings, time to solution, speed up, efficiency, whatever you put. But you should also put the real numbers in a table that are clearly available for inspection, not to be extrapolated by a plot, because sometimes this is really impossible. Or we could also suspect that this is due to, let's say, trying to hide some results. So log plots are also useful to spend many orders of magnitude. It's fine if you use them, but you should also put the raw data. And this is an example. So on the top, you see a weak scaling example. So the black line is the ideal scaling behavior, so perfectly flat. On the right side, you have the table with the data. So the number of processors, the time to solution, whatever unit you want, and then the ideal time to solution. So you can easily compute a speed up and an efficiency. And on the bottom, a strong scaling example in a log scale, and again, the table of data. It should be quite simple. It's perfectly feasible without consuming too many resources. So that's something that you should really invest time in, because that is really crucial to evaluate the real performance of your problem. And then the milestones, that's an important part in terms of project management. So goals and milestones of your project should articulate and should explain the simulation objectives, the objectives of your project in detail. And so they should measure, they should show how to measure the progress in your project. It is important to provide a connection between the milestones and the simulations that you plan. So you have objectives, but you also have a schedule, because you run simulation on a big system. So you should provide a chart, typically a Gantt chart, in order to clarify, to show the dependency and the matching between the objectives and the actual simulation plan. Because you need to take into account that all the centers are very busy in general, very used. Often you don't have, let's say, the possibility to accumulate resources and use all of them at the end of your allocation period. Typically, this project runs on a year, sometimes over 3 years. So you need to plan very well in advance your simulations, and that's why you need to have good milestones in order to show the progress, and you need to provide this schedule to help also the computing center see if your project has some bottlenecks, has some maybe breaks during the project development. At CSCS, for instance, we give allocations on a quarterly basis. So every 3 months, you have a chunk of your allocation. During the 3 months, you are expected to use it linearly. There is an algorithm then that gives you priority based on the usage. If you use it in a, let's say, weird way, in some different mathematical fashion, then you might get lower priority. And if at the end of the 3 months you haven't used the chunk, then you lose it. Because we cannot afford to keep the allocation if you're not using that for the whole year. So, because of fair usage. So that's the last point. Ensure that the core hour consumption is regular throughout the allocation. Provide a requested schedule after consultation with the computing center. Indicate the job sizes and the scheduling of computing tasks in your Gantt chart. That's also very important to let the committee understand that you know what you're doing, that you're not simply sketching a kind of fake project management plan, but you really know what is there. And also personnel plan. So personnel that will be hired for the project and the responsibilities is also important because you need people to run the simulations. The PI, the principal investigator, usually will not run himself, so he needs a group to do that. And he needs to plan also to have some, let's say, risk management there, because it happened in the past, it can happen that somebody leaves, so you need to have some replacement plan, some, let's say, plan B, let's say. At least you have to show that you have some kind of risk assessment here. So take into account also the potential personal turnover, specify if you have a team of collaborators, take into account possible conflicts if you have many collaborators, because sometimes there are conflicts depending on the fact that some reviewers might have been, some collaborators might have been previously reviewers, and so please read carefully the documentation that is available in the page, in the PRACE page, because there all conflict of interests should be actually declared. If you have a big team, this could be, let's say, demanding. And provide references to publications that acknowledge PRACE resources. So if you had previous allocations and you are submitting again, because as Grazia pointed out, this is the only way for the computing centers to show that their work is actually having an impact. So that's essential. That's the last slide that I mentioned before with the further information. So the PRACE application procedure, the link on top, where you can find all the information. Then the second link, the available Tier 0 supercomputing systems that were shown by Grazia in one of the previous slides, and will be up to date for the next call. Project scope and plan is the name of the template. So it's a docx document that you can download directly there. This has been updated after call 18. It might be updated when the new call 19 will be open, so you should download the one that will be the latest. The new call, as Grazia pointed out, will be open on March 5th. So please make sure that you don't use an outdated document, just use the one when the call opens, because you might have differences for each call. And then the last but not least, technical guidelines for applicants. This is a PDF that is also updated for every call. This one is updated for call 18, which is written in the link name. This lists all the systems with all the possible requirements in terms of storage, node job sizes, in terms of minimum allocation request, maximum. So this has to be read by the applicant before, of course, because you need to know what you're applying for. So I think that you will have the presentation afterwards probably, so you can also browse the links directly. I put the links in text so they are visible and just not clickable, so you can actually have a complete view of them. And I think I will leave space for questions now, because we have some more time.
For these kind of proposals. Are there still some questions?
just a Microsoft Office version.
Is
Of course,
the only one that will be accepted, or can I create my own template if it looks the same?
no, it will be accepted, but it needs really to address the same content, so the same section, headings.
Definitely.
Yeah.
Just asking.
I've seen that already, I think, in the past, and it's not a problem. Of course, they don't provide a LaTeX template, but if you can work yourself your own template, as far as the information is present, nobody will complain about which tool have you used to provide that. Yes, please.
Is there a guideline on how to make the trade-off between time to solution and parallel efficiency? Because you said it should be
Yeah.
the most efficient version for running the code.
That's in general a rule of thumb. So what we suggest for our national code in general is that, so once you start your scalability, we don't advise users to go over 50% efficiency, to go below 50% efficiency, because it means that you are communicating more than the computing. Because the part that is missing the ideal time to solution means that it's just communication in general.
The most efficient configuration in your slides is just as far as you can get improvements in your execution time and then stop there. Not that 100% efficient is.
No, okay, 100% efficiency would be very, let's say, very limited. So, of course, 100% efficiency is not achievable in general by many codes, so we would be very limited in the choice of possible. Usually people...
As an applicant, I could just have jobs that then run for several weeks instead of having a short turnaround time, therefore having better efficiency. If I use less nodes, then those nodes run.
Well, running several weeks is out of scope, because usually, for instance, we have a queue system that allows you 24-hour jobs. So several weeks, you mean with checkpoints, of course. Well, the point here is not what I mean by, so the compromise between parallel efficiency and time to solution should be a rule of thumb. I mean, there is no actual it's a mathematical formula that tells you if you should run at 80%, 90%, 60% parallel efficiency. Of course, you should also take into account your time constraints. If you want to achieve a certain result in a certain amount of time, then you will spend more resources, of course, and well, you will run with more cores and you will have less efficiency. I think this is, let's say, this is not stated here at which efficiency you should run, because it's left to the applicant, depending on the constraints of the applicant research. I don't know if I have replied to your question, but I think this.
So as long as you justify it reasonably.
Yeah, what I can say in the proposals that I've seen in the past, for instance, codes that can actually go at 60% efficiency, 55% efficiency. Sometimes they go a bit above 50%. They do that because, of course, they can run faster. They can get faster to the solution, although they are somehow, let's say, wasting some time in communication. But then, if you get half of the nodes and then you get half of the time to solution, maybe you're not in time in order to accommodate these simulations in your project management plan. So there should be some, let's say, consideration of your time constraints. You have, let's say, some research project, not only a computational one, but you apply for research funding, you need to produce some results, so you also need to know when you have to have the results. This should be also acceptable from the technical perspective, but as far as it is above 50%, I think nobody would complain.
But then the decision to actually make a checkpoint or not entails
far as you go, the risk is that you lose all the data. So if you don't have anything. So I think it's also in the interest of the production in order not to waste the resources that you already have consumed to have some checkpoint. I understand that terabytes of data is still an amount of dump that is allowed in stretch file systems. As far as then you can manage to move them as soon as possible, because of course, if you accumulate let's say if you arrive to hundreds of terabytes and then the time to transfer that is too long, you will lose your data. You have to consider that on the stretch file systems when you run simulation, you have also a cleaning policy. So after a certain amount of days, in our case 30 days, data will be deleted with no exception. So you have to take into account that the lifespan of the data in the file system running in production will be 30 days at maximum in our system. Then it's tightly machine dependent.
Okay. And the other question is regarding this indication of peak performance. I think our code calculates a lot, but much of it is actually also integer arithmetics, and so it does not probably perform not well according to this standard float thing. Is that something which is a disadvantage, or if one explains why the float performance? Because in the end, it still solves the problem. It's not,
let's say
the float is not the only thing.
No, I understand. I remember an example that was presented by some of the access committee members saying they were a bit disappointed sometimes to see in fact codes that are not using a good percentage of the peak performance. It's like you have a very fast car and you use it in the, I don't know, in the local streets here. That's let's say a very extreme comparison, but that's something that tells you if you have such a system, sometimes they are a bit disappointed to see that there are not so many usage cases that actually exploit this potential. For the moment, this information is optional, and I think as far as you can, you should provide that without being afraid of being penalized because of that. As far as the scientific problem is sound and the technical data is acceptable, I think you won't have to worry. Although you might be contacting me for improving, maybe there are alternatives that can use better the theoretical, if they can scale up to a certain, to a higher percentage of the theoretical peak performance.
Don't be surprised that they will teach you.
Okay, I don't know the specific problem, but might be, okay.
Okay, are there more questions? If not, then I thank both speakers again.